In this video, we'll be looking at this 6-layer mixed signal PCB, which is only 50 by 50 millimeters small, but packs quite a lot of different peripherals, both analog and digital. I'll walk you through the schematic, as well as the hardware design and the ordering process, as we need impedance control and a custom stack-up for this as well. Let's get started. Thank you very much to PCBWay for sponsoring this video. All future PCBs featured in this videos will be produced and manufactured and assembled by PCBWay. I'll also guide you through the ordering process, the files I had to submit, the documentation I made for this InfiniFX mixed signal 6-layer board, asking for impedance control, sending documentation, and so forth. Thank you very much to Altium for sponsoring this video. The PCB you're seeing this video I designed using Altium Designer, and I'll show you some of the cool things you can do with Altium Designer in this video as well. If you'd like to give Altium Designer a try for yourself, make sure to check out the link in the description below, or go to altium.com/yt/philslab to get yourself an Altium Designer free trial. Let's go through the design just as an overview. These are pictures I received from PCBWay for me to check after they'd assembled one board, to check the component orientations and placements to see if everything was in order before they continued with assembling the rest of the board. So this is quite a nice part of the process, and they made some pretty cool pictures. This is a 2-layer assembly board, so we have the top layer and the bottom layer. The centerpiece of this design is this STM32H723 microcontroller, very powerful, running at up to 550 MHz. A fair amount of flash and RAM, loads of peripherals, it's got caching, and loads of really cool things, so this is really a great starting point for any DSP application. The general idea of this board is predominantly for audio, in particular in my case for guitar, so digital signal processing, creating my own guitar effects pedal, so to speak, and this is the main processing and prototyping platform for me to do so. This is quite overkill in the amount of peripherals it has, so it has SD cards, USB high speed, and a lot more, which we'll go through in this video. But this is for me to check out which peripherals I need, if I'm getting the analog audio performance I want, and so on. This is a 6-layer board, and we'll cover that in more detail in this video. Anyway, moving on, we have our STM32H7 microcontroller, which is our DSP. It interfaces via I2S to the codec, which you can see on the left here, which is a 24-bit up to 192 kHz sampling rate codec. 2 channels in and 2 channels out. So it combines ADCs and DACs. We have a crystal, which is 24 MHz, feeding this STM32H7 for timing. On the bottom right, we can see this small QFN IC is a USB high-speed physical layer, which interfaces with ULPI to the microcontroller, and then on the other side, USB 2 high-speed. I also have an SD card reader, which is via SDIO connected to the STM32. I have this RS485 transceiver in case I want to expand, basically just a differential extension of UART. Top right, I have my preferred Tag Connect solderless programming header, which I can program by serial debug, a couple of LEDs, and various connectors. Bottom left connector is power. This board can take between 9 and 12 volts input, and from tests, it's about 2.5 watts that this dissipates, running a digital signal processing algorithm at full speed. At the bottom, I have essentially ADC connections to the STM32, which allow me to connect potentiometers, switches, and so forth, so I can change parameters on the fly. The top left section, we have audio input and output, 2 channels each, so left and right, with the SD card, and the top right, we have the RS485 connector. On the right side, we have this really cool mid-mount USB-C connector, which mounts to the middle of the board. So not top, not bottom, but middle. That's why I have this cutout in the way here. This also restricts the board thickness, so I can't just use a 1.6mm PCB. It has to be thinner than this to make sure this is centered nicely. Then looking at the bottom side, we have in the center this BGA package, which is SDRAM, which is connected via the flexible memory controller to the STM32. So this provides an extra 128 megabits of external memory. To the bottom right of this, we have a QSPI chip to extend the flash memory. I can also boot from this QSPI memory. We also see the bottom side and this cutout for the USB-C connect on the left, and to the right of that, it's a USB switch, which allows me to select between the full speed and the USB high speed. The only reason I included this was in case the USB high speed PHY didn't work, that I could simply switch over and just use full speed. In a finalized design, of course, I wouldn't include this. On the perimeters, we have various filtering circuitry as well as all the power. So we have power regulator on the bottom left, which is 1.8 volts, which is needed only for the high-speed PHY. Bottom right, we have 3.3 volts at 1 amp, and top we have 5 volts, which is then filtered and then passed to the top right, which is my analog section. So really, you can see quite a bit of sectioning going on. I've got memory, and on the bottom side, I've placed the BGA specifically underneath. I can just route underneath the microcontroller to the bottom, and my trace lengths are approximately all the same length, which means I don't really have to do any length matching for this RAM. I've sectioned it off so I have this compact grid at the top right, which contains all my analog circuitry, which is far enough away from my digital circuitry to minimize any noise and crosstalk. And given the board dimensions, which are about 50 by 50 millimeters, everything is really tightly packed. This is a bit more of a challenging design to make sure there's a nice interplay between analog and digital sections, as well as cramming all of these peripherals I can on this single small board. I wanted it to be this small so it fits pretty small guitar pedal enclosures, and I can use this in a variety of projects. But let's move over to Altium and look at the schematics and PCB design in a bit more detail. Here we are in Altium Designer, and I've sectioned my schematic into several pages, which I'd suggest for anything that's a bit of a larger project. So I have power, microcontroller, my memory section, USB high speed, peripherals, codec, and analog, as well as the main PCB file, and then some documentation. Let's start on this power section. I have a power input, some ESD protection, reverse polarity protection, and an input filter. I'm also essentially ordering this main power input, which would come from some sort of DC supply, with my VUSB filtered voltage with this Schottky diode. So depending if I want to use USB-C on its own, or if I just want to use a DC power supply, I can OR this with this diode. I didn't use switching regulators, despite for the 3.3 rail this would be more efficient, but because I want to absolutely minimize any noise within or close to the circuit, because we're in such close proximity. So all of these are LDO regulators at expense of efficiency. My main regulator for the 3.3 volts is a 1 amp regulator and requires only small input-output capacitors. Unfortunately, I only need 1.8 volts for my USB physical layer, so I have a small regulator to do that, with some suitable feedback resistors. And finally, I have my 5 volts, which is then filtered at the output to provide my analog 5 volt output. Now 5 volts is very low, and I had to choose suitable op amps and design the circuit suitably to make sure we can run off the low supply voltage, which we'll see in a later schematic page. For the analog section, it's usually fine to do this very crude RC low-pass filtering because the analog section typically only needs very low current. We won't get too large of a voltage drop across this 10 ohm resistor, and I'm using large 47 microfarad capacitors in parallel to give me a really low cutoff frequency to make sure any conducted noise coming from the digital side isn't passed over to my 5 volt rail and I get a fairly clean 5 volt rail. In addition, I'm adding quite a lot of resistance in the path of this 5 volt rail. Analog at this frequency is very low, only up to about 20 kilohertz, if not lower for guitar, and I don't need large current transients, and for the op amps I have local bypassing anyway. Moving on to the microcontroller section, unfortunately this symbol is a tiny bit messed up, so please excuse that. I've done my pinout using STM32Cube IDE, just selected my peripherals, and I've also color-coded my connections. So if I click on a net on the right in the properties panel, I can choose a color. And when we see later on the PCB document, this is really useful for distinguishing which sections need to route where and which sections exist where. For example, all the analog section might be yellow, and I can immediately tell in the PCB editor that this is an analog section. So loads of peripherals. I have my RAM, banks, I2C for configuring the codec, 3 LEDs, quad SPI, I2S, and many different signals. So it took some time to play around, finding what the optimal arrangement is, and some of this also changed during layout and routing. You can see various series resistors, for example this 33 ohm, and this is to reduce EMI issues or ringing, and I particularly like to place them on clock lines, so at the output of the transmitter. In terms of power and decoupling, as usual, it's one 100 nanofarad capacitor per VDD pin with a bulk capacitor placed somewhere close to the package. The VDDA voltage is used for the ADCs internally to the STM32, so that requires a bit more filtering. Then my JTAG connection, simply ESD protected, some minor filtering on the N reset line to prevent spurious resets, and that's about it. Looking at the memory page, this is my BGA IC for the memory, which is an ISSI memory part. It needs a fair bit of decoupling, again 100 nanofarads per VDD pin, as well as some bulk decoupling. On the left hand side we have the address, command and control signals, which I've indicated as color blue. We have our main address bits, bank address, and various control signals over here. This section you can see around these signals is called a blanket in Altium, and I've attached a parameter set to this to give it a net class name, for example. This allows me to see quickly in the PCB editor what the lengths are of all of these nets and see them as a group rather than individual items. In Altium I can also add various rules, for example that these need to be impedance controlled and so on, but as a bare minimum I will just put the net class name. The same thing out on the right for these RAM data lines. Essentially I have two byte lanes, one is the low D0 to D7 and one is the high byte lane D8 to D15. It's okay usually for RAMs to do bit swapping within the byte lane and do byte swapping. But for this layout, I didn't actually have to change any of these data bits. However, this can make your routing life easier. Moving to the right, we have the SD card, which is via an SDIO interface, so a 4-bit interface, including a command and clock signal, again using blankets and parameter sets, as well as this SD detect pin. I've placed suitable, fairly weak pull-ups on relevant lines, and of course provided some decoupling and bypassing to the SD card. Lastly, on the memory page, we have this QSPI flash memory, which I can use to store additional program information or maybe some sort of filter coefficients and so on. Now we come to the USB high-speed physical layer. There are many different physical layers ICs that will work with STM32 microcontrollers. One popular one is the USB 3.3 line from Microchip, which unfortunately requires 3.3 volts as well as an internal 1.8 core voltage. That's why we had that extra regulator. On the right side, these are the signals that go to the STM32 microcontroller, which can interface with the USB high-speed controller. So we have 8 data lines, clock, and various command signals, as well as a reset signal. On the other side, we then need a clock source, which I'm using a CMOS oscillator, again, decoupling with 100 nanofarads, because this is a switching part, and a series resistor to reduce ringing. This resistor I place close to the output of the CMOS oscillator. On the side, we have our USB high-speed differential pair, and I'm just using it in device mode, so I'm leaving the ID pin floating. On my peripheral page, I can see my USB-C connector. I'm leaving the shield floating. USB-C lines pulled down, which are the communication channel lines. And for really simple negotiation of power delivery, you have to pull these down individually with 5.1 kiloohms. And this can give me up to about 1.5 amps of current, which is plenty for this device. On the other side, my VBus voltage, I filter and pass to the Schottky diode on my power page, which we saw on page 1. Then I have my USB switch, which I can toggle via the microcontroller, which reroutes the connector, USB differential pair to the high-speed pins of the PHY or the full-speed pins directly on the STM32 microcontroller. On the peripheral page as well, we have the RS485 transceiver, which is essentially, in very basic terms, a UART to differential UART transceiver. I'm just using this as a point-to-point connection. So I have termination resistors on this side. Normally you can get away with just using a single 120 ohm resistor, but these pull-up and pull-down resistors of 390 ohms each make sure the bus is in a defined state at all times. In Altium, don't forget to make sure your differential pairs are labeled _P and _N, and that you add a differential pair directive. And I like to add a differential pair class name as well, which helps me with routing later on. There's also 4 ADC channels, which we saw were these control connectors. So I filter my 3.3 volts and pass it to each of these connectors, add ground to each connector, and also filter the ADC inputs with a small series resistor and a capacitor to form a low-pass filter. We're nearing the end of the schematic. One of the most important parts of this design was this codec, which is a Cirrus Logic CS4270 24-bit up to 192 kHz codec, so 2 ADCs and 2 DACs, connected via I2S to the microcontroller. I'm using I2C for configuration, so setting data rates and so on, and also have these address select bits for I2C. I'm just pulling them all down with 10K, and this sets the I2C address of this device. This codec requires several voltages, so we have the control voltage, we have the digital voltage, analog, and some sort of filtering banks, and this is all given in the datasheet and taken pretty much directly from there. The constraint of running the analog section of 5 volts is pretty much given by this codec. Of course, I could run the analog section following this, so the op-amps at a higher voltage, but this board was packed enough anyway to need another regulator. Then the outputs and inputs, we have 2 analog inputs and 2 analog outputs. For my input section, I have a 4-pin connector with suitable ground return paths. The left and right channels are pretty much identical. I have ESD protection, an RF filter with RT700 and CC700. This is a low-pass filter set at a very high cutoff, so usually around a megahertz or a couple hundred kilohertz. And this is to make sure any RF that's been picked up by the cable connecting to this device, that this RF isn't demodulated by any semiconductor nonlinear element. Since I need to bias my op-amps at half the supply rail, I generate a VREF, which I'll show you in a second, and bias with a high value resistor, since this is a CMOS op-amp and has a very low input bias current. So there will be virtually no current drawn through this RT702, so I can make this a large value. At AC, RT701 and RT702 in parallel are basically my input impedance, so that's 500 kiloohms. I need my coupling capacitor to make sure any DC isn't affecting each other. This is a simple unity gain follower. This TLV916 is a rail-to-rail input-output amplifier, and it's unity gain stable. And it also can run off a single supply rail up to about 5 or 5.5 volts. So these parameters are really important with such a low single rail supply voltage. Then a smaller amount of filtering. This codec luckily has quite a lot of anti-aliasing filters internally, and then a coupling capacitor going into my audio codec, and the same for the right channel input. The reference voltage is simply a potential divider, 5 volts, with fairly low value resistors, because the higher the value of the resistance, the higher the Johnson noise generated by those resistances. So I try to practice low resistance or low impedance design when it comes to analog audio circuitry. So 1K and 1K gives me 2.5 volts at Vref, and with some heavy filtering with this 47 microfarad capacitor. Looking at the output section, again 2 identical channels, output of the codec, coupling capacitor, again high value pull-up. This coupling capacitor and RT708, this pull-up, will form essentially the input impedance that this codec output sees, and will also form a high-pass filter, setting the lower cutoff frequency. Then I have a very simple high-pass filter, which is a very crude reconstruction filter. Again, a unity and gain buffer, so I can feed cables, a 100 ohm resistor to isolate the op-amp output and any inductance and capacitance of the cable, coupling capacitor, and a bleed resistor RT711, as well as some ESD protection. That's pretty much all there is to the schematic, so fairly simple, fairly straightforward, although there are quite a few peripherals. Let's look through the PCB design. And this is a 6-layer board, and 6 layers was because it's a fairly small design. I have some high-speed signals as well as all this RAM and memory to route out. In Altium, going to Design and then Layer Stack Manager, we can see the exact build-up of this PCB, and this is a fairly thin PCB. If I go to Panels, if I bring in the Properties tab, it's around 0.8 or 1 millimeters, so fairly thin. I'm using fairly thin dielectrics and fairly thin cores to get good coupling between the layers. My stack hop is signal, ground, signal. Effectively then it's a power layer. I'm not routing any signals on the power layer, ground, and a bottom signal layer. I'm also using impedance control for the USB high-speed stuff and some of the RAM connections. So I need 2 controlled impedance types of traces. One is 50 ohms, which using Altium's built-in impedance calculator gives me these values for microstrip and strip line, and I need differential 90 ohms for my USB differential pair. Again, centerpiece is this STM32 microcontroller, left-hand side the codec, right side all the digital things, such as the USB high-speed physical layer, USB-C connector, and so forth. Layer 2 is ground. Layer 3, we have some ground copper pores, as well as USB high-speed signals. Layer 4 is pretty much only a power layer. I have 1 polygon, which is 3.3 volts. I'm separating this with a ground pore with my fairly sensitive 5 volt analog plane, which is underneath the analog section on the top left of the board. Below that, I have another ground plane, and below that I have the bottom layer. Again, the coloring helps me out when routing. The top left I can see is yellow, which is analog. Then I have in the center my BGA memory IC, where I can see various pin banks, various data banks, address command and control signals, and so on. If I didn't have a color scheme, so pressing F5 on my keyboard, it looks a lot harder to see what is placed where. But turning on my colors, I can see immediately how I've sectioned my board. Routing wise, I've tried to length match for the USB physical layer, even though the constraints aren't that tight. I can go to my PCB section, ULPI, and again this was because of our blankets and our directives. You can see I've length matched pretty much exactly. I've also routed each signal pretty much the same way, so the same amount of vias per signal, so this isn't taken into account the delay, and they're all pretty much matched. I've tested the USB high speed and this works, so this seems to have been a good job routing this out. Also in layer 3 I have matched the lengths quite a bit, because the pin out of this STM32 microcontroller is a bit annoying. We have a lot of these USB ULPI pins at the bottom, and then this one single USB ULPI D7 pin at the top. So the pin out of ULPI for STM32 microcontrollers is pretty annoying, which means I have to increase the lengths of all the other traces to make sure that one pin is the same length as well. On the topic of length matching, looking at the fan out or the pin out of this BGA, we have various power pins, and we have address command control, data pins of one byte lane, data pins of the other byte lane. And for this, I really didn't worry too much about length matching given the speeds that we're running at. I also placed this IC directly below the STM32 microcontroller to make sure if I route underneath the microcontroller on other layers, the length or the delays to this memory IC are pretty much matched anyway. They're, plus minus 100 picoseconds, which is definitely within tolerance for this part. Any signaling and any high-speed signals in particular, you always have to make sure to have a ground plane underneath. I've also placed my vias in a way that I don't get too much ground plane voiding. If I had vias closer to each other, I'd have more cutouts in my ground plane. So if we zoom out, you can see my ground plane, although it has cuts in it from the individual vias that aren't ground, I've made sure to place 2 non-ground vias not too close to each other to cause cuts. So for example, these vias on the right, I've placed far enough apart so I get this sliver of ground copper pore flowing through them. Because this is such a tight and constrained board, it was hard to do proper separation between the analog and digital sections. My codec is half analog and half digital, so the top side is my I2S connection to the microcontroller, and the bottom side, a lot of these pins, but not all of them, are analog. The way I've tried to mitigate that is by doing some sort of copper stitching around this analog section and immediately coming out of the analog pins, routing onto a different layer. For example, the inner layer as strip line to make it as shielded as possible, and routing into my analog section, and keeping my analog section on the bottom side, so opposite to the microcontroller on the opposite side, away from digital ICs and away from the power section in its own little group, so very tightly spaced. I've made sure I've kept maximum distance I can, despite the size and the small size of this board. The separation and mixed signal design is one of the most important things. Not only XY, but also on the Z axis. So I could have put this on the top side, but I preferred to put it on the bottom side because I have various ground planes in between, providing extra shielding. I oftentimes also get asked if I have a multi-layer board with ground planes in between, do I fill in my signal layers with ground after routing? And the answer is it depends. In this case, I did, because large empty sections would have just been not filled with copper. However, you have to take into account a few things. To me, the sections have to be large enough to fill in, as well as far enough away from controlled impedance traces. If I were to route power or pour power right next to these controlled impedance traces, this would change the impedance properties. It would be a coplanar impedance profile instead. So I need to pull back my ground planes or my copper pours away from adjacent to these sides of these controlled impedance traces. On the bottom side, I've done something similar. So small patches I have filled in with copper, but I wouldn't just do one single copper pour over the entire signal layers. I do specific placement of small copper pours to make sure I'm staying away from controlled impedance traces, and I'm placing them where it makes sense and these islands aren't too small. Of course, this can't really be generalized too well and is pretty much scenario dependent. I prioritize routing out the buses first, so USB high speed, as well as all of my RAM and memory connections, because these just have the most pins. Also, of course, decoupling capacitors close to all the relevant devices, trying to maintain separation between analog and digital, and having some sort of neat placement of all components, as well as all the connectors around the perimeter. We look at this USB-C connector. This is a mid-mount connector, which I thought was quite cool. That's why I had to do this cutout in the board and make the board thinner than a normal 1.6mm board. All in all, from the tests I've done, everything is working so far, so I've programmed this device, I have the first few effects running, and we'll be using this in future videos on digital signal processing. And I'm pretty happy with the performance, also noise-wise. So layout-wise, I think I've done an okay job for now. When it comes to documentation, before I sent this off to PCBWay to have manufactured, I created the Gerber files, of course, pick and place, my bill of materials, but I also created a small hardware documentation, which can help with assembly and seeing how this board should look when it's assembled. In Altium Designer, there's a really cool feature called Draftsman. So I can right-click on a document, add new to project, and click Draftsman document. And this is a Draftsman document. This is updated anytime you make a change to the PCB. You can update the changes. You can add information on the board, for example, top and bottom realistic views. I've added that I need 6 layers, impedance control, and so forth. I can do isometric views for assembly. I can tell people about the stack up and what impedance profiles I need. I give a manufacturing overview of what layers there are to make sure the layer order is correct, say what drills there are in the design, and how the assembly is with component designators top and bottom side. And this is information I then also provided to PCBWay to aid them when it comes to assembly, and you would do that with pretty much any PCB manufacturer. With PCBWay, you can either use the standard PCB, but for more complicated boards like this, I would suggest going with advanced PCB. These all cost a tiny bit more, but the price difference actually isn't too bad, and you can have really cool options when it comes to PCB specs. For example, the IPC class, you can even do HDI boards, and you can have quantities as low as a single board made. Up to 60 layers, which is mental. I know this was a 6-layer board, thickness 0.8, and you can choose track spacings down to 3mm, which is less than 0.1mm. That's pretty amazing. Hole size, you can go pretty small as well, and solder mask, I use matte black with yellow silkscreen, which I think looks really cool. Surface finish default for advanced PCBs is ENIG, and I had to choose several extra options, for example, impedance control, because I want 50 ohm controlled impedance and 90 ohm controlled differential pair impedance, and I then also supplied a custom stack up, which will then also help you with and verify if this is producible. And then of course I chose assembly service, and this was a double-sided assembly board, and they sourced all of the components after me providing a bill of materials. From PCBWay or any PCB manufacturer where you can get impedance control, you might then get a document from one of the engineers giving a suggested stack up. This is for a different board, this is for an FPGA board, telling you, for example, what prepegs they might be using, what cores and so on, and telling you for outer layers, inner layers, strip-line microstrip for given impedances, what your trace width should be adjusted to. Now, you can either adjust that in your files as well, or let them adjust the trace width and so on. They'll also show you the various properties of microstrips, what the various dimensions should be. So that's really cool when you do impedance control. So the total cost for 5 boards, including all of the components, and there are quite a lot of them, a double-sided assembly, a 6-layer impedance controlled board with a custom stack up, this is about $1,100. For a prototype, I think this is really reasonable, so about $200, a bit more per board. Again, this is a fairly complicated advanced PCB. It took less than a month for me to actually have the boards in the hand after I had ordered them. And you can see the files I provided, so the Gerber, bill of materials, component placement, as well as additional documentation, which included information on the stack up, as well as this draftsman document I showed you. I hope this was a nice brief overview of the thoughts and schematic and PCB design that went into designing this small digital signal processing board. And this board we'll be seeing in future videos on digital signal processing algorithms, for example, guitar effects and so forth. I've tested pretty much everything on this board and everything seems to work well, so I'm pretty happy that it came out this way first try, and I look forward to working with this board in future videos. Thank you very much for watching this video. If you haven't already, please do subscribe to the channel to stay up to date with PCB design, electronics, and digital signal processing content. Thanks again, and I look forward to seeing you in the next video. Bye bye.